Ladies and gentlemen, on behalf of Associated Universities Incorporated and the National Radio Astronomy Observatory, a very large array, a very long baseline array, it's a great privilege to welcome all of you to the 28th Jansky Lecture. The Jansky Lectureship, which honors the founder of radio astronomy, Carl G. Jansky, is awarded annually by Associated Universities Incorporated in recognition of outstanding contributions to astronomy. It is a special honor this evening to welcome to Socorro Dr. David S. Heescheen, because without Dr. Heescheen's efforts, Socorro would not be the major center of radio astronomy that it is today. Dr. Heescheen's lecture this evening is the history of radio astronomy in the United States. He is particularly qualified to speak on this topic because he helped make much of that history himself. In the early days of radio astronomy in the United States, he was one of the first few people to earn a PhD in astronomy, in radio astronomy, from Harvard. Dr. Heescheen made significant early contributions to our knowledge of extragalactic radio sources. As director of the National Radio Astronomy Observatory for 16 years, he oversaw the design and construction of the Very Large Array, an instrument that has made tremendous contributions to the astronomical community. Dave Heescheen prefers to credit many other people for building the VLA, but we all know it stands today as a testimony to his leadership and dedication. Following his directorship of NRAO, Dr. Heescheen continued his career of scientific research, pioneering the investigation of the intensity variations of small amplitude and extragalactic radio sources, something that we call flickering. We seem to be doing some experiments with flickering this evening. Among Dr. Heescheen's many honors are the terms as president of the American Astronomical Society and a membership in the National Academy of Science. He's received several honorary degrees, and one that we know well here in Socorro is the honorary degree that he received from New Mexico Tech in 1989. At the end of Dr. Heescheen's lecture, he will take a few questions, and he tells me they are not allowed to be too difficult. And after that, I would like to invite all of you to join us in reception in the lobby here at the Mason Center. Please join me in welcoming back to Socorro Dr. Dave Heescheen.
Thank you very much, Miller. Somewhere I've got a clock. It's a great pleasure to be here. I've been here many times, but never in this capacity. It had been my original. Can we turn the lights up a little bit, please, so I can see the people I'm talking to, at least for a few minutes? I'd rather see you. It was my original intent to give you what I hoped would be the definitive story about not the history but the development of radio astronomy in the United States tonight. And that turned out to be far beyond my capabilities. So instead, I'm going to just intersperse some personal recollections and anecdotes with a little bit of selected history. And the result is going to be a incomplete, rather biased description of some aspects of the development of radio astronomy. And some topics that aren't going to be touched at all, like solar radio astronomy. And others, like the development of NRAO, are going to be over-described, probably. And finally, I'm going to stick to the period before 1975, and the theory that hardly anybody here can contradict me if I do that. So I will start with some history that you probably already all know, but it's pretty obligatory at the Jansky lecture to do it. The first detection of radio waves, as you all know from beyond the Earth, was made quite accidentally in 1931 by Carl Jansky, who was a radio engineer at Bell Labs. And while investigating investigating the properties of atmospheric static, he noted a Heescheen receiver that varied in intensity with the sidereal period of rotation of the Earth and peaked about in the direction of the galactic center. And he correctly deduced that this Hiss, as he called it, was coming from the Milky Way. Now, there we go. Now maybe we'll have to turn some of the lights down a little bit for a while. The importance of this discovery of Jansky's can hardly be overemphasized. It was the first of the new windows that were opened up on the universe at new wavelength ranges, and the subsequent developments have just enormously enriched our understanding of the universe. The next development came in 1937, when Grote Reber, also a radio engineer, built a parabolic antenna in his backyard in Wheaton, Illinois, and began observing the cosmic static that Jansky had discovered. His antenna was 31 feet in diameter. This isn't a very good picture of it, but there it is. It was a transit instrument originally, had a solid surface, and it was good at 10 centimeter wavelength. He built it all by himself. It was the first telescope built specifically for radio astronomy. And both the telescope and the results he obtained with it were pretty remarkable. He published maps of galactic radio emission, which weren't improved upon for many years. And it wasn't until 1953, almost 20 years after he built this, that a larger antenna with a more accurate surface was used in radio astronomy. So these two original developers or discoverers of radio astronomy were really remarkable guys, and set the stage for everything that happened after that. Post-World War II radio astronomy had its roots in the Jansky and Reber work, in the wartime discoveries of solar radio emission by Hay in England and by Southworth here in the United States, and by the wartime research and development of radar. The latter produced scientists and engineers who were skilled at radio techniques, and it also left behind a lot of surplus radar equipment that was readily adaptable for radio astronomy use. So soon after the war, Hay, Lovell, and Ryland in England and Pawsey in Australia began using the surplus gear to start the development of radio astronomy. And they quickly built up very active and productive groups around each of them. Some radio astronomy was done in the United States during this period from 1946 to 50, but the activity was minuscule compared with that in Australia and Britain. A few solar and galactic observations were made at MIT and at the National Bureau of Standards. But by 1950, only Cornell and NRAO were engaged in radio astronomy on any sort of a regular basis. At Cornell, the EE department there began radio astronomy in 1946. Probably the first institution here in the U.S. to get started in radio astronomy. The principal people involved were C.R. Burroughs, Bill Gordon, and Charlie Seeger. And I think the latter two, many of you are in the audience know. They designed and built a 17.5-foot parabolic antenna and also set up a 205 megahertz dipole array on a surplus radar mount. And later on, a variety of other meter wavelength arrays were built at Ithaca and at Sacramento Peak in New Mexico, where they set up a solar station for the Air Force. They were used primarily for a long series of solar observations extending well into the 50s. Unless you're a real aficionado of solar work, I don't think this work amounted to a whole lot. But it did lead ultimately to Arecibo and the NAIC. Seeger and Bill Gordon, the two people most involved, both got heavily involved in other aspects of radio astronomy, and Gordon ultimately went on and built Arecibo. I'll talk about it a little later on. So it was a very important early beginning to radio astronomy at Cornell. NRL's initial forays into radio astronomy consisted of observations of solar eclipses that were made at various exotic locations in the late 40s and early 50s. Their first observations were made from a ship off the coast of Brazil during the eclipse of 1947, and they were at 3 centimeter wavelength. These and some Russian observations at 150 centimeters were the first radio observations of a total solar eclipse. The NRL group was engaged primarily in centimeter wavelength radar development, and to apply their centimeter wave technology to objects other than the sun, and in particular to planets and to the so-called radio stars that had recently been found and about which very little was then known. They needed an antenna larger than the small radar dishes they've been using for the eclipse work. It happened that Ned Ashton, who later designed the NRAO 140 foot, already had in his back pocket, for reasons that I don't know, a design for a 50-foot diameter high precision parabola. NRL got that design and built it, mounted it on the roof of an NRL building in Washington, D.C. I knew I was computer illiterate, but I didn't think I would be remote control. That's the wrong one. That's the right one. This is the 50-foot dish. And anybody who flew into Washington and to the D.C. airports probably saw this thing that was there for a long, long time. The pointing accuracy of this telescope was very poor, but it was far and away the most powerful telescope available anywhere for centimeter wavelength observations, and it quickly proved its worth. The first observations with a 50-foot were begun at 9.4 centimeters in 1953. Haddock, Mayer, and Slonaker measured 6 of the brightest known radio sources and also detected emission from 2 H2 regions. These were the first centimeter wave observations of objects outside the solar system and the first radio observations at any wavelength of H2 regions. The telescope continued to be used for several years, but its poor pointing was a severe problem, and it was replaced in 1957 with an 84-foot dish with better pointing and a better sight. But the 50-foot played an important role and marked the real beginning of centimeter wavelength radio astronomy. It had some other curious effects as well. Its poor pointing was due in part just to a poor mounting design, but also in part to the difficulty of making analog coordinate conversions at that time. And this so scared people that when it came time to design the 140 foot, I'll talk about a little later, they didn't want an LS telescope. And this in turn led to all kinds of problems. In March of 1951, Ewan and Purcell detected the 21 centimeter line of hydrogen. And that's Ewan with his horn. The line was also detected almost simultaneously by groups in Australia and the Netherlands. At the time of the discovery, Ewan was a graduate student in the physics department of Harvard, and Purcell was his thesis advisor. The antenna they used consisted of this copper-lined wooden horn and was stuck out of the attic of the window at the Harvard Physics Lab. And that'll cause a short delay. I went to Harvard as a graduate student in the fall of '51, just 6 months after the line had been detected. And if there was any excitement over the discovery of the line, it apparently had subsided by that time. Because I can't recall any mention of it at the observatory that fall. But in the spring of 1952, a brash young undergraduate, Campbell Wade, who's still brash, but not so young anymore, thought it would be fun to learn to use Ewan's equipment. He went to Bart Bok, who was the astronomer at Harvard most interested in galactic structure and in the interstellar medium, and Bok went to Ewan. Ewan said it wasn't worth his time fooling around with just one lowly undergraduate, and he didn't even know Wade. Couldn't Bok find a few others who were interested as well? So Bok recruited 2 graduate students, Edward Lilly and me. Wade, Lilly, and I went to see Ewan in his gear, which is in the next slide. And we got all fired up at the prospect of doing 21 centimeter line observing. This is the inside of where the horn is, and the horn's connected to a waveguide. It's a slotted line waveguide, so you could do impedance matching with the halograph and the receiver here, and a few other things, and that's what he detected the line with. So when we wanted to start doing some observing, when Wade wanted to do some observing and Lily and I had to go along for the ride, Ewan is a real entrepreneur. He was then, and I guess he still is, and he knew how to respond when an opportunity knocked. He pointed out that it wouldn't be very useful original horn antenna, since the groups in Australia and Holland were already working with telescopes that had much better gain and resolution. So Harvard really needed a bigger antenna, and he just happened to have a friend who could build it. So Bach raised some money from a private source and also got a little money from the then very new NSF and contracted with Ewan's friends for a 24-foot antenna, which is in the next slide. As soon as the antenna contract was signed, Ewan announced that he was giving his radiometer to NRL and it wouldn't be available to the Harvard project. So Harvard had an antenna and no radiometer. But Ewan pointed out that a nice shiny antenna like this really deserved a better radiometer, and he had by chance just formed the Ewan Knight Corporation, which would be happy to build one. So thanks to one student's curiosity and the Ewan salesmanship, Harvard wound up with a 24-foot dish and what was then a state-of-the-art radiometer. That radiometer had 2200 K noise temperature. It was a single-channel scanning receiver. It took 8 hours to scan the available passband, and it was a real pair to use. The 24-foot dish is the same size as the subreflector on the new Green Bank telescope, or as a 100-meter telescope. The radiometer was built by Jack Campbell, who you all know is now here an engineer here in Socorro. And Lily and I provided the manual labor for the project, and Wade, as befits the instigator of it all, didn't do a thing, so I can recall. I told Campbell I was going to pick on him. That's the end of it, Cam. Carnegie, the Department of Terrestrial Magnetism at Carnegie, and NRL also began 21-centimeter line work at about the same time. Carnegie with a 25-foot dish, and NRL with a 50-foot that you saw a few minutes ago. Neither of those programs lasted very long. Carnegie moved its equipment to Argentina, and NRL turned its attention to other aspects of radio astronomy, as you all know. So there was a lot of early activity in the 21-centimeter line business, but not a whole lot actually happened in terms of contributing to the body of scientific knowledge with those particular antennas. DTM also built a Mills Cross, but a lot of people got their feet wet in radio astronomy and ultimately went on to do many other things. DTM also built a Mills Cross type antenna consisting of a couple of dipole arrays, each about 2,000 feet long, and they began observing the 22-meter wavelength, a very long wavelength, in mid-1954. And with that antenna, Burke and Franklin detected bursts of non-thermal radiation from Jupiter in early 1955. And that discovery sparked a lot of interest, and many others set out to confirm and expand on their work. Among them were Harlan Smith and Jim Douglas, who were then at Yale, Tom Carr and Alex Smith at the University of Florida, and Jim Warwick at Colorado. Smith and Douglas left Yale after a few years and went to Texas, where Douglas developed a big low-frequency array. But Florida and Colorado, those programs of monitoring Jupiter radiation went on for quite a long time. The only other radio astronomy program that began in the early 1950s was that at Ohio State, where Krauss built an array of helical antennas operating at 1.2-meter wavelength. His goal at the time was the study of galactic emission. The science produced in this early post-war period was, with a couple of outstanding exceptions, like the discovery of the 21-centimeter line, not of itself particularly significant, and it was largely overshadowed by the results from Britain and Australia. But it did get U.S. scientists interested and involved, and it paved the way for the things that were to come. And now, before turning to the next phase, which I think began sort of distinctly about 1954, let me briefly review the way radio astronomy has been funded. Most radio astronomy is funded by the federal government, and that's been the case really since World War II. And unlike the situation in optical astronomy, there have never been any large private or state-funded radio observatories. Two federal labs, the National Bureau of Standards and NRL, began in-house solar radio programs shortly after the war. Now, the first government agencies to provide funding to a university radio project were the Air Force Office of Scientific Research and the Office of Naval Research. ONR began funding the Cornell program right from the beginning in 1946, and the Air Force funded in 1948 the Solar Observatory, Radio Observatory on Sac Peak. The Air Force went on to fund a number of other solar radio programs, including those at Stanford and Harvard and Fort Davis. And the Arecibo 1,000-foot and the Haystack 120-foot were also originally funded by the Air Force, but for purposes other than radio astronomy. In the mid-1950s, radio astronomy programs were begun at Berkeley, Caltech, Florida, Illinois, and Michigan, and all were funded by ONR, the Office of Naval Research. The first NSF radio astronomy grant was for $32,000, and it went to Art Bach at Harvard in 1953 for that 24-foot telescope. And for the next 15 years, the NSF and the DoD provided roughly comparable sums. The open circles show the NSF's contribution to radio astronomy over the period shown from 1953 to 1975 or 4, and the filled circles show the Department of Defense's. And as you can see, they start out being approximately equal. But the enactment of the Mansfield Amendment in 1968 just dried up DoD support for radio astronomy. And the NSF became almost the sole source of radio astronomy funding. And that's pretty obvious, pretty clear from this make it work. There we go. That's pretty clear. The 1968 Mansfield Amendment, end of DoD funding, was phased out over just a period of a few years, and a sharp increase in NSF funding. The Mansfield Amendment prohibited agencies from funding science programs unless they were directly related to the agency's missions. And so ONR ceased its support of radio astronomy, except at NRL, which continued to be funded by the Office of Naval Research. ARPA ended its support of Arecibo, and the Air Force ended its support of Haystack. And all of these programs were taken over by the NSF, as were several of the university programs that ONR had been funding. NASA provided very little money to radio astronomy in the early years. It did, however, support the Clark Lake and Marfa decameter wave facilities and the Mont Blanc millimeter wave telescope, all in the 1960s. And more recently, it's provided considerable funding to Arecibo, Haystack, NRAO, and other institutions for facility improvements and equipment development. The next slide shows the total funding. From the beginning, sort of, federal funding from the beginning till 1978, where the NSF and others changed the way they were reporting things, and I detailed information about radio astronomy. But astronomy funding, from here, this was the radio astronomy expenditure in 1992. And you can see that the radio astronomy funding increased rather rapidly and leveled off around 1975, which was the first year of major VLA funding. And it leveled off during the VLA construction in here, and then began to decline. Sorry, up in here. This is the beginning of the VLA construction. So when the VLA started construction, the funding jumped and leveled off for a few years. And it's now down here. And the details of how it got from here to here, I don't know. But if you look at the total astronomy funding for that period, for NRAO, for grants, for everything, there's a general decline that begins somewhere along in here and just goes right on down. This is all in 1992 dollars. So the amount of money that's being spent on radio astronomy today, total, in 1992, is about the same as it was 20-some years ago. In terms of spending power. Well, I think 1954 marks the beginning of this new phase of radio astronomy in the United States. By that time, discrete sources had been identified with both galactic and extragalactic optical objects. It was was recognized that some of them were intense emitters of non-thermal radiation and that they had very unusual properties. Large catalogs of sources were being produced, and there was a lot of speculation and argument about their properties and their distribution in space. Much of this, or most of this work, was going on in England and Australia. The 5 modest programs that I've just described, at NRAO and Harvard, Ohio State, DTM, and Cornell, were, with the exception of the 50-foot, they were all operating with radio telescopes that were considerably less powerful than those elsewhere, and they just weren't contributing a whole lot. But it was clear that radio astronomy was a very rich field, that optical astronomers were beginning to take a serious interest in it, and there was a growing desire in the U.S. to get more involved. There was a 3-day conference in Washington in January of '54 that was sponsored by the Science Foundation, Caltech, and Carnegie. It was attended by about 80 people, including representatives from all of the major radio astronomy groups in Europe and Australia. It was an important conference. It was the first in the U.S. that was devoted to radio astronomy, and it served as a catalyst, I think, for many subsequent developments. It was the first opportunity for many U.S. science leaders to hear directly about the exciting work going on elsewhere and to meet some of the leaders of that work. During the next few years, and at least partly as a result of that conference, NRAO was created, and university programs were begun at Berkeley, Caltech, Illinois, Stanford, and Michigan, all in the space of just a few years. Next slide shows the table. What's going on?
Go back. You're going forward.
Go back. Thank you. I don't know what I'd do without the audience. This table shows the major U.S. institutions and radio telescopes at 3 different epochs. In 1953, there were just the 5 that I've described a little bit. By 1963, there were 19 different institutions that were operating radio telescopes in the United States. And several of those telescopes were as powerful as any in the world. The Arecibo, for example, the 90-foot interferometers at Caltech, and the 300-foot in Green Bank. Several telescopes came and went between 1963 and 1993, and therefore don't appear in this compilation at all. And since 1963, only one new institution has gotten into the radio telescope business and stayed there. That's UMass. And quite a few have dropped out, so there's a lot fewer institutions now than there was in '63. This decrease in the number of both telescopes and in the number of institutions operating telescopes and developing equipment began in the 1970s. I think the principal reasons were the high cost of doing forefront radio astronomy, the concentration of money and observing power into a few systems, especially into the VLA and the VLBA, which was beginning to be developed then, and the general decrease in radio astronomy funding began in the mid-70s, as we saw on the previous slide. In optical astronomy, there's many telescopes still operating that are far less powerful than the 200-inch or Keck telescopes, and this just isn't the case in radio astronomy. Small, less powerful radio telescopes have generally been closed down as new ones came into operation. There's a couple small ones on here, a couple of 85-foots that are just barely continuing to operate in 1993, but that's all. Some of those telescopes could still be doing very useful observing if the money to operate them was available. A lot of people deplore this situation, but I think that in a world of finite and declining funding for radio astronomy that we saw, I'm not so sure it's all that bad. It's probably contributed to the success of radio astronomy in getting the newer and more powerful systems that we've gotten. Some of the programs and telescopes deserve to be shut down no matter how much money was available. And the institutions and the telescopes that have survived this shakeout now provide the most powerful collection of radio telescopes that's available anywhere in the world, and they're available to all of us. So it hasn't been all bad. Although the number of institutions building and operating radio astronomy facilities and equipment is small, and it's considerably less than it was in the 60s, as you can see, The number of institutions with faculty and students that are engaged in radio astronomy observing has grown enormously in this same period. For example, in 1963, I think there were about 50 people from 25 institutions who were doing observing. And today the numbers are more like 400 people from 90 institutions. It's a bit of an estimate, but it's not off by more than astrophysical accuracy. Now this has come about largely because of the existence of NRAO and the National Astronomy, NAIC, the National Astronomy and Ionospheric Center, whose instruments are fast and powerful and are available to scientists from any institution. Furthermore, under pressure from the NSF, universities with major facilities now grant time, at least in principle, to visitors. And this trend began in the 70s and has extended to other countries as well. We all know that everybody goes everywhere to observe, and that was not true in the 50s. I think this is an important and it's a somewhat unanticipated result of the National Center concept. When I like to describe some of the programs that today provide the bulk of the observing facilities, the ones that are still left in 1993, and how they got to where they are, and especially NRAO. But first, let me say a little bit about Bell Labs, which has played a really unique role in the development of radio astronomy. Not only was Jansky at Bell Labs, but so was Southworth when he detected radio emission from the sun. And then in '65, as you all know, Penzias and Wilson discovered the 3-degree microwave background radiation using a 20-foot long antenna. So Bell Lab scientists have been responsible for 3 of the most important developments in radio astronomy. And Penzias and Wilson and their colleagues were also active in the 60s in a completely different way. They developed some of the best millimeter wave detectors then available and used them with great effectiveness on a 36-foot to discover many new molecular lines. So this small group of just a few people has really had an enormous impact on radio astronomy. The 4 major programs that have been in business since the late 50s are Cornell and its operation at Arecibo, Caltech, Berkeley, and NRAO. And between them, they've built up and now operate most of today's radio astronomy facilities here in the United States. Berkeley began a 21-centimeter line program in 1958, and by 1960 had an 85-foot dish operating at Hat Creek. Their project, like Harvard's, was begun by an optical astronomer, Harold Weaver, and to study galactic structure in the interstellar medium. The telescope was used extensively, primarily for H1 and OH surveys, until it was destroyed in a freak windstorm last year. John Bolton came from Australia to Caltech in 1955 to start a radio program there. Caltech and Mount Wilson astronomers were already heavily involved in the optical identification and study of radio sources. And Bolton built a variable spacing interferometer of 2 90-foot diameter dishes, and it went into operation in 1958. Bolton didn't invent aperture synthesis, but his interferometer was really the forerunner of all later aperture synthesis instruments, including the VLA. And it soon produced a flood of new and important results. In 1962, Moffett and Maltby published results of a study of the radio structure of about 200 sources. They observed the several baselines and did both model fitting and Fourier inversions to obtain their source structures, and this was the first definitive study of source structure. A few years later, Cambridge, to be chauvinistic for a few minutes, a few years later, Cambridge published a similar study with the new 1-mile telescope in Cambridge. They had a lot more sources than Moffett and Maltby, but in fact didn't discover much that was new about the nature of source structure. What they did do, however, was publish contour diagrams for about the first time. And not only that, but they distorted the coordinates so the contours, so that the sources always looked circular, no matter what shape the beam was from their east-west interferometer. Caltech, however, had simply published a table with the source parameters in it, and the Cambridge impact in a way was much greater, visually much greater, but there wasn't any more information in it. The first 21-centimeter line interferometer was also done with a Caltech interferometer. And in 1968, aperture synthesis observations of spiral galaxies, mainly by Rogestad and Shostak, showed pretty conclusively that H1 extends far beyond the optical limits of the galaxies, and that the rotation curves remain flat as far out as one can be detected. So these were the first observations that really provided direct evidence for the existence of large amounts of dark matter in these galaxies. This interferometer continued to produce important results for many years. In 1968, Caltech built the 130-foot dish. It was intended to be the first of an 8-element aperture synthesis array, but the others never got built, and today the 130-foot is used primarily for VLBI. Berkeley and Caltech both started millimeter wave programs in the 60s, which have now become their primary activity, and I'll mention these a little bit later. The NAIC is managed by Cornell. The main telescope is the 1,000-foot at Arecibo. Bill Gordon, who had been active in the first Cornell project in the 40s, was the inventor of the Arecibo 1,000-foot. The original motivation for it was ionospheric studies, but its potential use for radar astronomy and for passive radio astronomy was recognized from the beginning. Gordon wanted collecting area for his ionospheric work, and to get as much as he could for his money, he chose a fixed reflector pointing to the zenith. He made the reflector spherical so he could get some steerability just by moving the feet around. To get reasonable sky coverage with this limited steerability and to cover the ecliptic, for planetary radar purposes, he wanted it to be at about 20 degrees latitude. And to further keep the cost down, he wanted to find a natural hole in the Earth in which to set the thing. Well, it turns out that this site near Arecibo, that's that one you know. Site near Arecibo fits all those criteria, and this is the telescope for the result. The telescope was funded by ARPA and the Air Force. It went into operation in 1963 and has proven highly successful in all three areas of research: ionospheric, planetary radio, radar, and passive radio astronomy. After passage of the Mansfield Amendment, the NSF took over its support, and at that time the NAIC was formed. Prior to that, it was just a Cornell project. The telescope's surface accuracy and stability were improved in the late 60s, and another major upgrade is in progress today. I think Arecibo has been a great success. It's been providing unique capabilities for 30 years, longer than any other telescope in the world. It's proven to be particularly important for extragalactic 21-centimeter line studies and for pulsar studies. If there's going to be another Nobel Prize for radio astronomy anytime in the near future, I think it's most likely to go to Joe Taylor of Princeton for his work at Arecibo on pulsars. I wrote that 3 months ago when I first started work on this talk, and then I went on to describe Taylor's work. And I guess that isn't necessary now. It has been in all the newspapers recently, and so I was a good predictor of the obvious, I guess. Discussions that led to the formation of the NRAO began in 1953 among scientists at Harvard, at MIT, NRL, and a few other places in the East, maybe. The Radio Astronomy Conference in January of '54 provided further impetus. And in April of '54, Donald Menzel, the director of Harvard Observatory, asked AUI, Associated Universities Incorporated, to develop a plan for a cooperative radio observatory. AUI is a consortium, of 9 Eastern universities. It had been established in 1946 to manage Brookhaven, a high-energy physics lab that operates accelerators and reactors for use by scientists from anywhere. And it was exactly the kind of operation that the group at Harvard and MIT had in mind for a new radio observatory. AUI held a conference in May 1954, attended by just about everyone in the country then active in radio astronomy, plus many optical astronomers and radio engineers. The conclusion of the conference were that the general idea was good, that AUI should get money from NSF to do a feasibility study, and that the principal telescope should be a large spherical parabola. AUI submitted a proposal for the study to the NSF and then set up a steering committee to guide the study. In March of '55, the steering committee made a formal recommendation that the major instrument be a reflector of at least 600 feet in diameter. 4 months later, the same committee, exactly the same membership and everything, issued a second report, this time recommending that the major instrument be a 140-foot parabola. A change from 600 feet to 140 foot for the main telescope apparently came about as a result of the reaction of an NSF advisory panel on radio astronomy that was chaired by Merle Tuve, the director of the Department of Terrestrial Magnetism at Carnegie Institution. The NSF panel thought that the Marsh proposal, which besides the 600-foot included a 150-foot dish and several 60-foot dishes, was just too ambitious. AUI was instructed to concentrate on a more modest plan and give particular emphasis to a telescope of 140 feet in diameter. And exactly how the 140-foot size came about, I haven't been able to determine. Because earlier they talked about 150, which is a rounder number in a way than 140, I guess. AUI complied, but this 600-foot telescope remained a major goal of AUI and NRAO, actually, for a long, long time. AUI submitted a plan for a radio observatory to the NSF in August of '56, and that plan included designs for a 140-foot, but not for any other telescopes. Also included in the plan were proposals for site buildings, for facilities, staffing and organization, operating policies, and a budget. The whole works for a new observatory. Well, there followed several months of sometimes acrimonious debate about the proposal, and especially about who should be the manager, AUI or some other organization. And this argument really boiled down to a disagreement between Lord Berkner, who was president of AUI, and Merle Tuve, who was the director of DTM, over what the observatory should really be. Berkner wanted it to be a big institution, like Brookhaven, which would provide extensive facilities and services for visiting scientists, and would also have its own scientific and technical staffs engaged in their own research and development. Tuve, on the other hand, wanted it to consist just of a telescope sitting out in a field. No staff, no facilities, no services, just a telescope. They was prepared even to camp out in tents. And in anticipation of this style, DTM had already built a hydrogen line receiver into a trailer so they could move it around to various telescopes, including the new one that was going to be built by NRAO. Berkner was the prototypical big scientist of the time. He had been president of almost every international and national scientific organization that had anything to do with this field. He was the prime mover in inventing the International Geophysical Year and getting it going. He was just a big scientific politician. Tuve was the prototypical string and ceiling wax scientist, and he ran DTM on a minimal budget, and they did everything themselves. It was good, old-fashioned, solid science. They were both geophysicists. They worked together either during or before the war, and they apparently developed a mutual dislike and distrust way back then, which was thoroughly exacerbated by their totally opposite approaches to science. The management argument was finally decided in favor of Berkner and AUI, as you all know, but this question of how big NRAO should be and just what it should do remained a major issue for a long time, and it still persists to some extent today. The selection of Green Bank as the site of the proposed observatory was much less controversial. The NSF advisory panel had already decreed that the site should be within 300 miles of Washington. Now, why this arbitrary decision was apparently accepted without any challenge, I don't know. But once the decision was made, then the choice of Green Bank was simple. It was hands down the site. In November of 1956, a contract was signed, and I think I have a picture of that memorable time. There it is. On your left is Lloyd Berkner, the president of AUI, and on your right, sitting beside him is Alan Waterman, the director of the National Science Foundation, and they're signing the first contract that brought NRAO into existence in the fall of 1956. The contract called for site acquisition and buildings, and for the construction and operation of a 140-foot telescope, but it made no mention of any other telescopes. In fact, both the 85 and the 300-foot telescopes were built before the 140-foot was completed. Now, let me get one more slide in here. This was a dedication of the observatory done at the time of the, shortly after the signing of the thing. And it's the pictures of a little bit of interest because of the people involved. The fellow on the far left here is Dick Emberson, who was assistant to the president of AUI. He did all of the initial planning and studying for the NRAO, almost single-handedly. He did a beautiful job on everything except the 140 foot itself, which was a total botch. Next, like Berkner, the president of AUI. The fellow sitting down, you all recognize as John Finley. The man beside him is Ned Ashton, the designer of the 140 foot. That's me, and I don't remember who that and that are. So, by 1958, just a year later, the concept of what was big had gone from 600 feet to 140 feet, and the concept of what was going to be off the shelf just to get the observatory going had gone from 140 feet to 85 feet. So we built the 85-foot telescope. It went into operation in 1959, and very shortly after that, Drake did his Osmond experiment with it. Now, I'm running pretty late, but I'm going to show a few slides of the early time of NRAO. This is the dedication of the 85-foot telescope with Otto Struve, the full-time director of NRAO, and Lloyd Berkner, president of AUI. This is the site, probably about 1961. It's a little bit of interest. The 140 foot is under construction here. This is the first 85. This building housed the scientific staff, which consisted of Finley and Drake and me and a couple of technicians. And I don't remember whether Hogg and Wade lived in this building for a while or not. Over here, you can hardly see it, but I'll show another picture later, is a 5-foot dish, which was the beginning of millimeter wave radio astronomy at NRAO. And this is where old astronomers went. Well, I don't have time for this, but anybody who wants to see this later on, they can see it. This is the first Russian-American joint conference on radio astronomy. I guess I do have time for it. It took place in about 1961. There's Lloyd Berkner. This is V.V. Bakevich, who was the leading observational astronomer in the Soviet Union at that time. This is, I've forgotten his name, this is Kuzmin, another Soviet astronomer. And there's a bunch of Americans here that you'll recognize. Sanamayan, another Armenian astronomer, radio astronomer, is here. Fred Haddock, a brash young astronomer. And so on. Charlie Seeger, the man that started off things at Cornell. So there's a lot of interesting people here. Well, let me get to that. AUI had begun design of the 140-foot telescope in 1955 under the guidance of the steering committee. And many, many problems were encountered in both the design and the construction. And what had started out to be a quick off-the-shelf telescope that would get the observatory into business and serve until the 600-foot was built turned out to be a lengthy and costly project. It was finally completed in 1965 at a cost of about 3 times the original contract price. And because of the delays to the 140-foot, NRAO acquired the first of its 385-foot telescopes and the 300-foot, all in an effort to do something while this 140-foot was being built. And the 140-foot, when it finally was completed, turned out to be quite a useful instrument, and you know it's still doing good work today. But the misadventures of the 140-foot strongly influenced the way subsequent major projects were handled in NRAO, in particular the BLA. In 57 and 58, when all these problems with the 140-foot were going on, things looked pretty dark. We weren't getting anywhere with the 140-foot. The NSF had no interest in this 600-foot telescope that was supposed to be the centerpiece for NRAO. NRAO wasn't functioning as a national center. Elsewhere in the United States, hardly anything seemed to be happening except at Caltech, where the interferometer was just getting underway, and that was clearly going to be a major instrument. And in comparison, radio astronomy was flourishing in Australia and England. And this frustrated feeling is what led to the 300-foot. NRAO submitted a proposal for the 300-foot in 1958. And the specs called for a 300-foot diameter telescope operating at 21 centimeter wavelength with good sky coverage, should be cheap, and should be acquired in 12 months. It was expected to be used only for about 5 years, after which it would be replaced by the 600-foot telescope. Bob Hall did the basic design of the 300-foot over a period of 2 or 3 weeks. Hall had earlier designed the 85-foot while he was working with Knox, and later on he went on to design the 36-foot while he was working with the Rohr Corporation. And today he's the NRAO's project manager for the new Green Bank telescope. The 300-foot was completed in the fall of '62. And the whole process from concept to completion took about 4 years, and I think that's a record short time for a major telescope that may never be broken. The 300-foot continued in use for many years, and I'll show these pictures. As you know, it's ultimate history. Skip that. There it is one day, and there it is the next day. So the telescope that was designed for 5 years lasted 26, and finally expired in the manner shown. Good things can come out of this, even, as you know, because it was a result of this that NRAO got the money to build the new Green Bank telescope. NRAO moved its headquarters from Green Bank to Charlottesville in 1966, and the decision to move, not to move, but to where to move, was one of the most heavily debated ones both in NRAO and in the AUI Board of Trustees that I can recall. It created far more discussion and controversy than any scientific or technical proposal we ever made to the board. It was generally agreed that NRAO headquarters should be on or near a university campus. And there were 3 possibilities that were considered: Morgantown in West Virginia, which is the only university of West Virginia, Charlottesville, where we finally wound up, and a more distant intellectual center like Princeton or Columbia or Harvard. We chose, I don't have time to go into the reason, we wound up choosing Charlottesville. Many of the Board of Trustees wanted Princeton or Harvard or Columbia, depending on where they happened to be from. Not really true. They had reasons for wanting it. But there was a lot of argument about it, and ultimately, as you know, we moved to Charlottesville. In retrospect, this period from about 1960 to 1970 was extraordinarily busy at NRAO. The 300-foot got built, 3-element interferometer was built at Green Bank. We started millimeter wave astronomy, built the 36-foot on Kip Peak, moved the headquarters to Charlottesville, designed the BLA, and started the OBI, and established NRAO as a functioning national center, which was accepted by and extensively used by the scientific community. The intensive work of the 50s and 60s to find radio sources and measure their positions and radio properties took place primarily in England and Australia, but it had important consequences for radio astronomy in the US. It stimulated lots of optical work on identifications and redshifts, primarily at Palomar, but also at other big optical telescopes. It stimulated the construction of big antennas at Ohio State and Illinois, and it was a major stimulus for the establishment of the Caltech Owens Valley Observatory and of NRAO. Bott and Minkowski published their famous papers on identification of sources in 1954. And the identification of SIG-A was with this large redshift optical object was especially exciting. They pointed out that the radio emission of Cygnus A was greater than its optical emission, and that objects like it would be observable at radio wavelengths at distances far beyond where they could be seen optically. And then in 1963, Schmidt showed that the radio sources that had recently been identified as star-like objects were in fact extragalactic, now called quasars. So by 1963, the extragalactic menagerie was essentially complete. And there were these three kinds of extragalactic source. The strong radio emitters identified with peculiar galaxies like Cygnus A, strong radio emitters identified with quasars like 3C273, and the much weaker radio emitters identified with ordinary spiral galaxies like M31. That's been expanded and modified a bit since, but basically that's the way it was then and really still is. The further understanding of these objects and how they fit into the overall scheme of things has been one of the main efforts of radio astronomers for the succeeding 30 years and has driven many of the major instrumental developments. The radio galaxies and quasars in particular exhibited a very wide range of properties, and it was clear that there was a need for radio telescope systems of much greater resolution and sensitivity than were currently available. And out of all of this came the Caltech 130-foot, the VLA, an upgraded Arecibo, and VLBI. The Whitford Committee, which was the first of the so-called decade reviews of astronomy, published its report in the summer of 1964 and recommended the development of a powerful instrument with 10 arcsecond resolution at centimeter wavelengths and about 1 arc-minute resolution at 21 centimeters. It also recommended that the instrument be built and operated by the NRAO. Now, this was an important report in that it gave, for the first time really, some sort of official community endorsement to a very sophisticated, powerful telescope to be built and operated as a national facility by NRAO. The panel also recommended expansion of the Caltech interferometer by adding 6 130-foot dishes to the 2 existing 90-footers that were there, by construction of 2 fully steerable parabolas of about 300 feet in diameter at unspecified locations, and construction of 15 smaller special purpose instruments. Their cost estimates were way out of line, but their recommendations were pretty good. The Whitford report gave impetus to various plans for new instruments that were already in progress. That's where they got the ideas in the first place, from the plans that were already in progress. And by 1967, NSF was faced with proposals for 4 new telescopes and an upgrade of Arecibo. The 4 new proposals were for the VLA from NRAO, for an 8-element array of 130-foot dishes from Caltech, for a 135-meter diameter parabola to be built in a radome from NRAO, a consortium of New England observatories that was set up explicitly for that proposal, and a 100-meter diameter parabola to be built on the west coast, and again a new consortium called ARA, Associates for Radio Astronomy, was set up for that. The latter consisted of Caltech, Berkeley, Stanford, University of California, and Michigan, but really was Berkeley. And so the NSF set up a committee chaired by Bob Dickey of Princeton to advise it about all these proposals, which added up to a lot more money than NSF could imagine spending. The Dickey Committee met in 1967, had exhaustive hearings and exhausting hearings, and wound up recommending that Arecibo be upgraded, that the Caltech array be built, that the VLA and the 135-meter dish be further studied, and they rejected the 100-meter dish. The 100-meter dish was a favorite of Harold Weaver at Berkeley's. He got Caltech to join him, but Caltech was afraid that being part of 2 proposals would hamper their efforts for their array, and so their support of this 100-meter dish was worse than lukewarm. It was almost negative during the hearings, the Dickey Committee hearings, and I think to a considerable extent as a result of this, that dish was rejected. Well, nothing happened after this for 2 years. Nothing happened at all. And so the Dickey Committee met again in 1969, and this time they recommended that everything be done. Arecibo, both arrays, the Caltech array, and the 135-meter dish, and the VLA. And they didn't set any priorities, they just said do it all. 2 years later, the Greenstein Committee came into existence. That this was the second decade review committee following the Whitford Committee. And by that time, only the receiver upgrade was in the works. So the three remaining projects, the two arrays and the 135-meter dish, fought it out all over again, and this time the VLA emerged as the clear winner and received first priority, not only among radio astronomy projects, but among all astronomy projects. So work on the VLA, I think that since I'm at the VLA, I'll skip everything else about the VLA. You know all about it. You know it's there, it does good things, but even the VLA can't do everything. It doesn't have as high resolution as it's needed for some problem, and it doesn't operate at millimeter wavelengths. The need for higher resolution has been a dominant theme in radio astronomy since the beginning, really, and the ultimate expression of that is very long baseline interferometry. And the development of high-quality magnetic tape recording systems and accurate clocks in the 60s made it feasible to record the output of individual antennas on tape along with timing signals, and then bring the tapes together somewhere and correlate them to obtain interferometer fringes. I think it was far easier to do the correlation then than it seems to be today. This with pre-antenna separations in interferometers from the constraints imposed by cables or by radio links and let you have much higher resolution. Three groups began development of such systems in the mid-60s. The University of Florida group built a system operating at 18 megahertz to study Jupiter bursts, and a Canadian group and a joint Cornell NRAO group each developed systems for the study of discrete sources. The Cornell NRAO group consisted primarily of Cohen and Jansky from Cornell and Clark and Kellerman from here at NRAO. All three groups achieved successful results at about the same time in 1967. Getting the equipment working and the telescopes all pointing in the same direction at the same time was quite a problem at first. In the early days, were noted for frayed tempers and enormous telephone bills, as I recall. But very long baseline interferometry soon expanded to include telescopes in Europe and the Soviet Union, with resolutions up to a milliarc second or so. And this kind of resolution has produced remarkable results, as you all know. Using antennas with widely different characteristics, sometimes with widely different receiver capabilities, and having access to these telescopes, typically 25% of the time or so, causes scientific limitations and frustrations. And to overcome this, the idea of a dedicated array for long baseline interferometry was conceived very early by the people doing the VLBI work, and particularly by Kellerman at NRAO here and by Cohen at Caltech. So designs were developed at NRAO and at Caltech. NRAO received the NSF funding in '84 to build a VLBA, and again, I don't need to continue that at this site. Now, the other thing I mentioned that the VLA doesn't do is observe at millimeter wavelengths. Millimeter astronomy was developed first primarily in the United States, and although it began early, there were observations made in the 50s. It's only been in the 70s that this wavelength regime has really come into its own. The University of Texas, the Aerospace Corporation, NRAO, Berkeley, and Caltech all began millimeter wave work in the 60s. Texas built a 16-foot dish on the campus at Austin in 1963, which was later moved to Mount Locke, where it operated until the mid-80s. The project was originally under the direction of Straighten and of Charlie Tolbert, who's now at the University of Virginia. Vandenbout took it over for a number of years, and that work contributed considerably to the development of molecular spectroscopy. Aerospace started their millimeter work at about the same time Texas, and I think their 16-foot dish, which was on the roof of a building in downtown Los Angeles, I think it was the same dish, essentially, as that at Texas, both of them built by Philco Ford. And it was used primarily to study the variability of discrete sources, and it ceased operation in the mid-80s. Berkeley and Caltech both developed millimeter wave facilities in the 60s, and as you know, they're both operating nice millimeter arrays now. I don't think I have time to, I'll have to skip that, and let me say a little bit about millimeter wave radio astronomy at NRAO, which began in 1961 with Frank Drake and Frank Lowe. Lowe at that time was at Texas Instruments, and he was just beginning development of liquid helium-cooled germanium bolometers. At NRAO, Frank Drake obtained one of Lowe's bolometers and a 5-foot spun-cast dish. I have a picture of somewhere. to skip a lot of slides. I'm way behind times. Sorry about that. One reason I'm behind is I don't know how to work this thing. There's the 5 foot. This was the first millimeter wave telescope at NRAO. And Drake used it for a little while with Lowe's bolometer. And then Drake urged Lowe to come to NRAO, which he did in 1962. And Lowe used this telescope to observe the moon at 1.2 millimeters in 1962 and 1963. Well, Green Bank isn't a very good site for millimeter wave work, most of the time anyway. And a 5 foot dish is pretty small. In January of '65, Lowe and Davidson went to Palomar and observed 3C273 and 3C279 with a 200 inch. These were the first observations of discrete sources at 1 millimeters, and they were the first, and I think the only radio astronomy observations ever made with a 200 inch. Planning for a larger dish at a better site began in 1962, almost as soon as Lowe got to NRAO. And in '64, we had a contract for a 36-foot telescope with the Rohr Corporation. 2 sites were considered, Mount Lemmon and Kitt Peak, both near Tucson. Both had about the same weather and seemed equally suited for millimeter wave work from that point of view. Kitt Peak was chosen finally for 2 reasons. First, there were existing support facilities there that were already being used for astronomy, and we thought we could take advantage of that and save some construction and better yet, operating costs. And perhaps more important, Mount Lemmon was just loaded with other kinds of transmitting antennas that we were afraid were a potential source of severe interference. Rohr had a lot of difficulty fabricating with 36 foot, and especially machining the reflector surface. The reflector was machined as a single unit, and transporting it from the Rohr plant in San Diego to Kitt Peak, to the top of Kitt Peak, was also a problem. But eventually it was completed and it went into operation in '68, just in time to play a big role in the explosive development of molecular spectroscopy. In 1983, a surface was replaced by one slightly larger, 12 meters in diameter, and more precise. The possibility of detecting spectral lines at radio wavelengths from other atoms and molecules besides H1 was discussed in the early '50s by both Shklovsky in Russia and by Towns in the US. Deuterium and helium-3 were considered the most promising atomic candidates, but neither has yet been positively detected, although there have been a couple of suggestions. The only other atomic lines that have been found are the recombination lines of hydrogen and a few other atoms. Molecules are another story. Shklovsky and Towns both suggested in the '50s that the hydroxyl radical OH might be detectable at a frequency of 1665 megahertz, and the lines, was detected by Weinberg et al. In 1963 using the 84-foot antenna at Millstone Hill and using his then relatively new autocorrelation receiver that he had developed while he was a graduate student for MIT working with NRAO. In 1968, Towns and his colleagues detected a line of ammonia with the new 20-foot antenna at Hat Creek, and a short time later they also found a line of water. Both lines were detected in emission at wavelengths near 1.25 centimeters. These discoveries precipitated an enormous and ungentlemanly rush to see who would be the first to detect which line next. The next line to be detected was formaldehyde at 6 centimeters by Snyder and Buell in '69 using 140 foot. And this was the first complex organic molecule to be detected, and it further fueled the competition. Most of the observing was done with NRAO telescopes and radiometers, the 140 foot for centimeter wavelengths and 36 foot for searches at millimeter wavelengths, because these were the most powerful systems available. So all of the competitors were using the same equipment. And the competition boiled down to choosing which line to look for, which frequency to look at, and where to look in the sky, and most of all, depending on luck with the scheduling and with weather and equipment. And it must have been obvious after the first few lines were detected that there was no longer much glory or academic tenure to be gained by detecting another. But they kept trying, and the competition was fierce for several years. The first thing a person did when he or she arrived at the 36 foot or the 140 foot for an observing session was to try and find out what previous observers had been up to by searching observing logs and quizzing telescope operators. We tried to institute rules about observers doing only what they said they would do in the proposal. And as you can expect, these rules were, well, they were certainly unpalatable, they were largely unenforceable, and they were very much ignored. There was a lot of fussing about scheduling. The NRAO got a bad name every time somebody thought he should have detected a line first rather than somebody else. And there was a lot of fussing about lost time due to weather and how it would be compensated for in the next observing run, if at all. And to equipment failure and about claim jumping and stealing of ideas. And some old friendships were strained and lasting animosities were generated. That was quite a wild time, I thought. But in the end, when all the dust had settled, a huge number of new lines had been detected, and molecular line radio astronomy was firmly established and flourishing. By 1972, there were 49 lines from 25 molecular species that had been detected. So that's a period of 4 years. And today there's more, as you know, there's more than 1,000 lines and 60 molecular species that are observable. What else? It's about time to quit. I think radio astronomy has obviously enjoyed enormous growth since the early 50s. And this growth was driven by interest in the wealth of scientific problems and by the various discoveries. And it was made possible primarily by these amazing technological developments that have occurred. Telescope collecting areas have increased by a factor of about 100. Radiometer sensitivity per frequency channel or unit bandwidth has also increased by about 100. The number of channels has gone from 1 to thousands. Resolution has increased by 10,000, and so on and so on. There have been comparable growth in data handling and analysis capability. And radio astronomy has both benefited greatly from these developments and contributed to them. But other factors also aided the rapid growth of the 60s and 70s. There was a time when federal support of science was growing very rapidly, as we saw, and the NSF was growing very rapidly and hadn't yet developed the sort of bureaucratic rigidity that eventually organizations achieved. And university astronomy departments were also growing very rapidly. And all of this, I think, contributed to a favorable climate for the developments in radio astronomy. And the years from 55 to 75 were exceptionally productive. They produced an expansion in scientific discoveries and technological developments and telescope power that I think isn't likely to soon be equaled. Today, the nature of radio astronomy has changed, and the climate in which it's pursued has changed. It's a mature field, very different in many ways from what it was 30 or even 20 years ago. The rate of growth has slowed, at least for now. Observing programs are usually aimed at more specific questions than at exploration. Observing techniques and data analysis become more complex, and partly as a result of this, people tend to specialize more and to work more in teams. But the scientific questions being asked today are far more sophisticated, and the telescope's far more powerful than 20 or 30 years ago. So the future, while it's going to be different, it's going to be surely no less exciting. I was going to show, hoped I was going to show 2 slides to help illustrate the difference between now and then. I couldn't find the slides or didn't try hard enough or something, so I'll have to describe it visually. The first slide is of a group photograph of a astronomical conference in about 1930 or so. There's 15 or 20 astronomers there in dark suits and ties and white shirts. They're all elderly. There's a couple of women in long dresses. The second slide is of an astronomical conference today, where there's 150 to 200 people. The people are all under 30. Their clothes don't bear talking about. You can't tell the men from the women unless you look real close. And yet, so there's a big apparent difference. But a lot of it, except for the difference in age, which it seems to me to be quite real, and in numbers, from a few to a lot, which also seems to me to be quite real, I think a lot of the differences are superficial. And people don't change that much, that quickly. And I think a lot of the differences between today and yesterday in science, in radio astronomy, are also rather superficial. Well, I have to close. You should never give up an opportunity to plug your next project. I have to skip on slides. Which you won't miss. Oh, that one I don't want to skip. You should never give up an opportunity to plug your next project. And NRAO has two right now. One is the Green Bank Telescope being built, already being built, so it doesn't need selling, but I'll show it to you anyway. This is an artist's conception of it. You all know all about it. It's going to be the greatest thing to come along in filled apertures in a long time when it works. And here's what it looks like as of last month. The tower, which is being used for construction, is almost 500 feet high, to give you some idea of the scale. It's an enormous thing. So that's the first of the next generation of telescopes. And the second is one you're all very familiar with and happy with, and that's the millimeter wave telescope. And I show it to you, even though you know far more about it than I do, because if you want to have it next year or the year after or 10 years from now, you got to plug it every chance you get. Show it to everybody everywhere. Thank you.